Consider the velocity time graph below and answer the questions below. So let's look at the motion that's described here. So we're going to start at some fixed point O on a straight line. And initially it's going to be at rest. And it's going to accelerate in a positive direction until it's going 10 meters per second. So it's going to accelerate out here. And then it's going to go at a constant speed of 10 meters per second. So let's just do that in a different color. So we'll do that here. And then it will continue to travel in the positive direction because the velocity is positive, but along here it's slowing down to rest. And that would be this section. So all of that, it's traveling this way. Now what starts to happen? Along here, it's accelerating, as in getting faster, but in the negative direction. So it's starting to travel backwards this way. Then it's going to travel at a constant velocity for a short time. And then finally, it's going to be slowing down, but still traveling in the negative direction because the velocity is negative. And it'll end up at some point here. So that's the overall motion. It travels out and it travels back. Okay, so we're asked to calculate the acceleration along each section of the graph. So what I'm going to do is label the sections A, B. This is all one straight line, so C. You can see that it doesn't change gradient somewhere. I'll call this D and E. And along A, the change in velocity is 10 over the course of 5 seconds. Now remember, that's an acceleration, so that is in meters per second squared, since the velocity is in meters per second and the time is in seconds. Along the section B, it's going at a constant speed, and therefore the acceleration is 0. Now along C, the change in velocity is negative 15. It goes from 10 down to negative 5. And that happens over a period of 5 seconds. So that is negative 3 meters per second squared. Along D, the acceleration once again is 0 because it's going at a constant speed. And along E, the change in velocity is 5, positive 5, because it's going from negative 5 to 0. And that happens over 5 seconds. So that's 1 meter per second squared. We now want to calculate the final displacement of the object after the 20 seconds of motion. Now, area is what's going to give us displacement. So the area of this triangle is a half times 5 times 10. That's 25. Then got this rectangle, which is 3 times 10, so the area there is 30. And then this triangle here, well, we need to figure out where that point is. And we can use similar triangles to do this. We know that it's gone 1, 2, 3, 4, 5 across, like so. I just paused and actually drew that a bit better. So that goes 5 across. And it goes down 15. Now, that 15 split into 10 and 5, which is a ratio of 2 to 1. So if we split this 5 into 3 parts, so each of those parts would be 5/3, it will have done 2 of those across in doing this section of line. So it's going to go across 10/3. And of course this is at 8. So that means that we've got 8 plus 10/3, which is 8 plus 3 and 1/3. So this point here is at 11 and 1/3. So for the area of that triangle, we're going to do a half times 3 and 1/3 times 10. And let's just do that on the calculator. So we're going to do 1/2 times 3 and 1/3 times 10, and that gives me 50/3, which is 16 2/3. So that's the area for that bit there. And then if we want this triangle just here, then the base here would be 1 2/3, which, remember, together with this 3 and 1/3 gives us 5, and the height is 5, so that's going to be a half times 1 2/3 times 5. Again, let's use the calculator to do that. So that's going to be 1 2/3 times 5, and that's 25/6, or 4 1/6. So let's just make a bit of space here, and we can say this triangle here is 4 1/6, and then we've got a rectangle which is 10, 2 times 5, and then finally we've got 5 and 5. Half of 5 times 5 is 12.5. Now the thing to remember is that all of the ones up here are while we're moving away. So all of those are going to be positive. All the ones below are when we're moving back. So the final displacement is going to be 25 plus 30 plus 16 2/3, take away 4 1/6, add 10, add 12.5. So let's put that into the calculator, and we have 25 add 30 add 16 and 2/3. We'll take away 4 1/6, add 10, add let's put that into the calculator. So I've got 25 add 30 add 16 and 2/3, and we'll take away 4 and 1/6, add 10, add 12 and a half. And that gives me 45 meters. And then in C, we want the total distance covered in the 20 seconds. Now remember, at the beginning, we looked at the motion and it traveled outwards and then back. And the outward distance was these three here. And the return distance was the contents of this bracket here. If we want distance, it's just going to add instead of subtract. So the distance is going to be 25, add 30, add 16 and 2/3, add the 4 and 1/6, and 10, add 12 and a half. So we're just going to add those all up to get the distance. So if we just go back to our calculator, all I need to do is go back to here and change that to a plus, and that gives me 98 and 1/3 meters. So we want to sketch a distance time graph, and note that is distance time and not displacement time for the object over the 20 seconds. So I'm going to do a sketch, but I've got a grid paper here, so I'll at least get some parts of it accurate. So after 5 seconds, we know it's traveled 25 meters. So that would be here. Now, think about what's happening. It's getting faster as it goes here, so it's covering more distance in shorter time as it gets towards the top. And that means that we're going to get a curve there. Now, once it gets here, it's going to be a straight line on our distance time graph because it's going at a constant velocity. Now it travels 30 meters, which means that in total it's going to be 55 by the time it gets to 8 seconds. Now that does indicate that I've got it a bit steep in that bottom section because that's a straight line section and that gradient would be consistent there. So I'm going to just change that bit there. Now if we add on this next section onto the 55, that's 71 and 2/3, and we know that happens at about 11 and 1/3. So 71 would be about here, and during this time it's slowing down to rest, so it's going to do something like that. And then in the next little section we're going to go another 4 and 1/6 meters up, so on this scale, and of course that takes us across to 13 seconds as well. On this scale that's not going to be very much, it's only going to go to here, so it's going to start to speed up there, and then it's going to go 10 meters in the next 2 seconds, so that's going to take it to about here, and then finally it's going to go 12.5 meters in the remaining 20 seconds. Remember the total distance was 98 1/3, which I'm going to say is about there on my graph, and of course it's slowing down during this section, so it must go like this. It's quite a difficult thing to draw, and you just need to take it a step at a time if you get something like that.